Welcome to this video of the demonstrator that concludes the antenna channel harmonization for throughput enhancement in Advanced Mobile Terminals project. My name is Ivailo Vasilev and I have my colleague here, Jonas.
Hi, Jonas Lindstrand here. First of all, we would like to thank our funders, Vinnova, the companies within the SOS Center, and also a big special thank you to Sony.
We start by showing the setup. This measurement is performed in a shielded room to avoid any frequency band licensing issues. What you just saw was the terminal in Jonas's grip. Then we have the 4-port VNA used for the propagation channel measurement. This red cable you see going on one side to the terminal, and then on the other side to the digital control board is actually used for controlling the tuners. These are it's basically done in a microprocessor programmed in C to clock the data and clock signals to the tuners so that we can select the proper states. This is the computer used for recording, post-processing and plotting the data in real time. The blue cables are used for the TX. The antennas themselves are located on a tripod, and the antenna type is a wideband monopole based antennas used to essentially emulate base station behavior. Next we show a better resolution picture of the RX prototype with the tuners in position located right next to the antenna elements. The antennas themselves are IFA based antennas working in the 800 MHz band with a bandwidth of 70 MHz, isolation of 6 dB, correlation of 0.4 in free space, and efficiencies of about -3 dB. Next, Jonas will describe the principles of operation of the tuner and the initial results.
The impedance tuner system consists of three 5-bit switch caps, C1, C2 and C3, and also two off-chip inductors, L1 and L2. Below you see the chip photo of the switch cap circuit. The area is 0.8 by 2 millimeters square. The digital control used to control the individual switch caps consists of drivers with variable on and off voltage, and also a serial to parallel converter in order to control the individual switch caps. Here we show the coverage of all the impedance states at 845 MHz. The tuner has a loss of 0.76 dBs at 700 MHz, and as you see at 900 MHz we have an insertion loss of 1 dB. To make the prototype more realistic, we added a battery board which contains battery holders and also voltage regulators in order to feed the right supply voltages to the impedance tuners.
At this point we show a front and back picture of the prototype and the grip in more detail with the batteries in position. It's a tight grip with two hands used for video, browsing or surfing the device. We now switch to a live feed from the screen of the demonstration software. This software is custom designed in LabVIEW and is used to control the VNA and the digital control board, as well as to record post-process and plot the results from the measurements in real time. In the boxes below we set the impedance states for the tuners per cycle. Each of these cycles is hard-coded to 11 states, where the first one is the 50 ohm state, and this is the case for all the measurements we perform today, excluding the finer grid resolution measurements which we do at the very end of this video. The final results from each of the measurement cycles will be displayed on these indicator boxes that the cursor is showing right now. These are the 50 ohm capacity, the maximal capacity, the capacity gain in dB and in percent. The two figures that you see right now are the matching states figure and the real-time capacity figure. They show the current impedance state tested and the corresponding capacity result for this state. Both of these figures will evolve in real time as the measurement progresses. We'll now go ahead and actually start the software. At this time we would like to emphasize that for the purpose of this demonstration video, We have speeded up the measurement and post-processing cycles in order to be able to present a number of relevant cases for a relatively shorter period of time. In reality, each of the 11 impedance state cycles takes roughly approximately 35 seconds to measure, post-process, and plot. The first measurement we will perform today is a free space measurement of the reference prototype. This prototype does not include any tuners and is manufactured mainly for normalization and comparison purposes. We do 2 consecutive runs, which is 22 states in total, in free space, and then we introduce 2 hand grips to essentially prove the huge drop in capacity, which is approximately 5 bits per second per hertz in this case. At measurement point 44 on the real-time capacity curve, we swap prototypes, and now we use the actual tuner prototype where each tuner is set to 50 ohm. We start with 2 cycles in free space, and then we do 2 cycles in 2-hand user scenarios. At measurement point 88, we already start varying the impedance tuner position, but before that we note that there is a very good match between the reference and the actual tuner prototype. And now at state 88, you see that the green markers indicate the current state being tested, while the red one will indicate the optimal state. And at that optimal state we have a 2.5 dB gain corresponding to 21%. Now we do another run with the exact same states for repeatability purposes, and we see that both the capacity curve and the optimal state remain the same. The actual values from this measurement are also similar to what we have obtained before. The next run will be with a finer resolution around the optimal state, and in this case we see that we can actually get an additional improvement of approximately 1.25 dB, corresponding to an additional improvement of 10%. So essentially, to conclude this brief demonstration, we have seen that we can go from approximately 6 bits per second per hertz to approximately 8.4, which is a gain of 40% in total, corresponding to an overall improvement of 3 dB in terms of power. With that, we'd like to thank you for watching. Stay tuned.